Good day everyone. This is the first video lecture on the topic analysis and calculus. Wait, why are we doing sets here? Now, analysis and calculus are things that we do with limits. Let's don't say analysis, just calculus. Now we do limits, we do differentiation, derivatives, integration, and all those fancy stuff in calculus, right? Got a bunch of them. But what are they based on? They're based on the existence of functions, right? If we don't have functions, what are we going to do with differentiation and integration, right? Based on functions. What are functions based on? Numbers, right? If we don't have numbers, we do not have any relationship between these numbers, right? These relationships are then called functions. Right, we're relating one number to another. Let's say function x squared, f of x equals x squared, means what? We are relating an x to its squared term, right? To its square. It means we're relating to two numbers, right? So that means we have to get somehow a closer look to these numbers before we get into functions, and then we can proceed into calculus and finally analysis. Right? So, still, why sets? Now, the first kind of numbers we have ever encountered is the so-called natural numbers. Right? Someone would say it's positive integers, someone's gonna say it's non-negative integers, including 0, right? But that's unimportant over here. No matter it includes 0 or not, the first number we're ever going to encounter is the number 1. And then we're told 1 plus 1 equals 2, 1 plus 2 equals 3, 1 plus 3 equals 4, and so on and so on. We got an addition table that you have to memorize, right? And then we go on to multiplication and then subtraction, and then all the time we're staying within the non-negative numbers. And then in secondary school we learned negatives, so then we can extend things, right, into the other side of the number number line, and then together what do they form? Right, as well we also learned fractions, we learned pi, we will probably learn something else, but some other numbers, but now we're staying in pi's, square root of 2's, square root of 5's, cube root of 3, right? We still do things with -1, -5, -10, positive 100, and all those stuff, right? What are these called? Real numbers. They're called real numbers. So, first part of every single thing in this series, in this analysis and calculus video lecture series, we are going to deal things with real numbers first. And now when we talk about real numbers, we usually like to talk with sets, right? We're going to talk about the real numbers as a whole, which we're going to say it's a real number set. Now I'm going to assume that you already know the terminologies and those basic operations, like unions, or to a more basic perspective, you know how to describe a set. You know how to add sets together, unions. You know how to make a difference between those two. You know how to you know what is a complement of a set inside another parent set, and so on. I mean, or superset. And then you also know subsets, supersets, proper supersets, and so on. Then what else are there in sets? What else are there in sets that you have to know here? Boundaries. It's boundaries. If you've known your statistics course, you know we can put data together and we form grouped data, right? We form grouped data. When data are grouped into groups, what are they called? They are called, yeah, of course, grouped data. They're called group data, of course. But we can also say these groups are sets, right? They're a bunch of things, pile of things put together, still, right? From a basic sense. If you're putting things together, you form a set. right? So in statistics, we know we know these grouped data. We got what? We got class mark, right, which represent the entire group. Of course, in sets we got the symbol, right? We can say this set is called set A, we call it set B, that acts something similar to class mark, as in statistics, right? Then we got what? We got class limits and class boundaries. Right, we got class limits and class boundaries, so there must be something analogous to this in sets, right? Then you say, it's gonna be the maximum and minimum. What's hard? Okay, define a maximum and minimum then. Maximum is going to be what? Literally, in a literal sense, maximum of a set is going to be the largest element in the set, right? That means anything else inside the set is going to be smaller than or equal to that number. So, if we have a number, there exists this reflected E, like if this is a mirror, you write an E, they just simply you reflect the E over the mirror to get the symbol. This is called there exist. If there exists a number, say capital M, inside a set S, such that no matter what else you take in the set, that thing that you take in the set, that else thing you take in the set, is going to be smaller than or equal to this M. Then we are going to say M is the maximum of the set S. Right? So similarly, if we have a small m, not a capital M now, if we have a small m in the set, such that no matter what you take, what else you take in the set S, in the same set S, this x is going to be larger than or equal to this small m. Then we're going to say what? We're going to say the small m is called the minimum of the set S. Right? Remember, maximums and minimums has to stay inside the set. Now, then we're gonna say, if both maximum and minimum exist, of course, then we can say, no matter what you choose in X, in a set S, this X is gonna be smaller than or equal to the maximum, and it's gonna be larger than or equal to the minimum. Right, which is intuitive. If you have a maximum, then nothing's gonna get larger than the maximum. If you have a minimum, nothing's gonna get smaller than the minimum, right? Now, what if we have things like this? Like, let's say we have a set A. It's defined to be 1 over x, and x is positive. It's every single number called 1 over x, where x is a positive number. Is there going to be a maximum? No, right? It gets larger and larger. It can get as large as you want, right? As long as you take x as a very, very, very small number, small positive number, a number that is positive and very close to 0, right? Like say 0.000001. That's 5 zeros after the decimal point. That means it's gonna be 1 over, how large is that? 0.000001. That decimal is gonna be 10, 100,000, 10,000, 100,000. It's gonna be a million, right? 1 over a million, that's 0.501. And then we're going to take 1 over that, it's going to be 1 million, right? It's going to be very big. And then if we increase the amount of zeros after the decimal point and then put a 1 after that, and take that as x, then x over 1 is going to be very large. It can get as large as you want, as long as you increase this amount of 0 after the decimal point, and you take that number as x, right? gonna get very, very large. But can it get small? Can it be negative? No. But does it have a minimum then? No, it does not. Because why? Why don't we have a minimum? Because there's nothing in the set that can... No, there's nothing inside the set. Such that no matter what you pick in the set, the number is always always smaller than or equal to x, right? Let's say you have you don't trust me and say there should be a minimum and it's gonna be 0.1, which is 10 or 1 over 10, right? That means you're taking x equals 10 here and say that this is going to be the minimum. Nothing's gonna be smaller than 1 over 10. But is it? Is 1 over 10 really the smallest element? No, because we got what? We got 1 over 11. We got 1 over 12. These two are apparently smaller than 1 over 10. Right? If you know 1 over 10 is 0.1, and 1 over 11 is what? Is 0.090909 and so on. Let's just take an approximation 0.09. It's already smaller than 0.1. Right? So, how do we say that it's not gonna be smaller than a number, but this number is not the minimum of the set? Then we're gonna say this number is called a lower bound of S. Right? No matter what you choose in S, as long as you have a number, I'm gonna skip a line here, as long as you have a number L such that no matter what you choose in S, the number that you choose is always going to be larger than or equal to the L. Now I'm not restricting this L inside the set already. Inside the set, it's not inside the set, but if you can still find a number that achieves this, then we call L is a lower bound of S. Right? Intuitive. If you have a number so that everything in the set is larger than or equal to that number, the number is then gonna be called a lower bound, right? Intuitive. Then similarly, we can get the definition for an upper bound. Say it's U. Then nothing in the set is larger than the upper bound, right? If it's an upper bound, it's something that's gonna like fix the set inside the region, right? If it's a bound, it's an upper bound. That means nothing is gonna get larger than this number. So everything is smaller than or equal to this number. Then we say U is an upper bound of S. Then there will be a problem here, not a question, sorry. There will be a problem here because there can be an infinite number of upper bounds once you found one upper bound, right? Let's say you found let's take back this A as an example here, right? 1 over x. We found 0 as a lower bound, right? 0 is a lower bound. Everything is larger than 0. -1 can also be a lower bound. Everything is larger than -1. -2, lower bound. -3, lower bound. A negative number, still a lower bound of S. Then how many negative numbers are there? Infinite. There's an infinite number of negative numbers. Right? Then that means there are an infinite number of lower bounds. Right? Then how can we straighten this? Now this is kind of important. If we have a lower bound, then there's gonna be an infinite number of lower bounds. If we have an upper bound, then there's gonna be an infinite number of upper bounds. Then how can we straighten this? Because say when we do with 1 over x, Let's graph it out. You know we can draw graphs, right? 1 over x, where x is positive, then that means it's this region. Right? Just this part, this gray part. If I'm gonna choose x equals -1 as a lower bound, then look, there's this big pile of area here that has nothing to do with the set. The set is this gray line. Right? This gray line is the set. But the green area does not have anything to do with the set. Then what can we do? Because this green part has nothing to do with the set, so we probably want to want this green area to become 0. We don't want this area to exist. Then what can we do? Then I'm gonna find this element here that makes what? Make this green area disappear, of course. And for now, I'm just gonna tell you that this element here that I find is 0. This number that I find is 0. 0 is going to make that element, that area disappear. If you don't believe me, you can increase this number and say 0.01. See? There's a small amount of this gray area over here, gray part over here, that is to the left of this blue line. That means this blue line cannot be a lower bound because there's something that's to the left of it, right? Left of it. So still, if we draw it, if it's here, then it's only because of the graph that is not shown properly, right? So no matter which positive number you choose, no matter how small it is, how close to 0 it is, as long as it's positive, it's not gonna be a lower bound. That means we have something that we can say about 0 here. 0 is the largest lower bound. It's the largest lower bound. And it's also the lower bound that does what? That does not give us this green useless part. Right? We can have a more clear, more accurate range that describes everything in S. Right? So we call this largest lower bound an infimum. Okay, let me move this up. Still, I'm gonna skip a line. If we have, what do you call that symbol? A symbol which is hard to write. It looks like this. Very hard. I'm not good at writing. What's this symbol called? Xi? Was it? I don't really remember, but that doesn't really matter. We have this number such that it's the lower bound of S. Let's say this is in the set of all lower bounds of S. No, let's just directly say it's the largest among the lower bounds. That means we're taking the maximum of these lower bounds. Then we say this thing is called an infimum, I-N-F-I-M-U-M. Infimum. This is shortened as INF. It's gonna be INF of S. It's gonna be defined to be the maximum of the lower bounds of S. Then what does that mean? Can we have a stricter definition for this infimum stuff if I don't want to find out the set of lower bounds? Similarly, now we can name also something else. The minimum of the upper bounds, right, leads to the same result. Can we not find the set of upper bounds and lower bounds of S to find the infimum, and what is called this minimum, the smallest upper bound stuff, is called the supremum. Supremum spelled this way. Is there any way we can just directly use elements in S, in a set S, to determine the infimum and the supremum without needing to know the set of lower bounds and the set of upper bounds of the set S? Yes, of course. Of course, we do. Now suppose we will deal with supremum first. If we have a number, let's say upper bounds, let's say u1. If we have a number u1 such that let's say if we have a u1 such that it's an upper bound for all x in S, u1 is an upper bound, so u1 is going to be larger than or equal to x. This is the definition of an upper bound. Right, then we have to demonstrate this minimum here, right? What does minimum mean? It can't get smaller. Cannot get smaller means what? Not being able to get smaller means what? It's an upper bound that cannot get smaller. Once it's small, it's not an upper bound anymore. Means what? Means when you have a positive number when subtracted from this supremum stuff, like when you decrease a little from the supremum, there will be something inside the set that gets larger than the number, right? Means if we define some positive number, define a positive number, say epsilon, there's gonna be something in the set such that when we subtract a little bit from this upper bound, we are gonna get less than this thing in the set. Then we're gonna call u1 is exactly the supremum. Then this is actually an extension of this minimum stuff, right? It does not have to be in the set, and it also describes perfectly the range of the elements inside S, right? Without needing to include things that are outside of S, right? So similarly, we can define infimum as well. If we have a lower bound L1, oh wait, this I should stricten it. If we have this, for all there exists a u1 larger than or equal to x. Let us move these further. Larger than or equal to x, such that there is a y here, right? Then this is the strict definition of supremum. Excuse me, my bad. Similarly, because we have to demonstrate it's an upper bound before everything. If for anything in S, there's the number L1 larger than or equal to x, such that, wait, do we even need this part? Anything that it's smaller than, it gets smaller than something in this. Yeah, we have to have this maximum part there and minimum part. So there's something that we add. If we're gonna add something to this lower bound, it's gonna be larger than something in the set, right? If we add something to one of the lower bounds of the set, it's gonna be larger than something in the set. Then this lower bound is gonna be called an infimum. An infimum is the largest lower bound, right? That means, excuse me, right? That means when it gets larger, when this number gets larger, it's not gonna be a lower bound anymore, no matter how small the increment is, right? So there we have supremum and infimum. We have a defined supremum and infimum, which is something that is more useful than a maximum and minimum, because not every single set has a maximum or a minimum. So we need the help from supremum and infimum to more accurately, when we do not have a maximum and minimum, to more accurately describe the set, describe the range of a set. Now there's something to notice. If the maximum exists, then the maximum is gonna be the supremum. If the minimum exists, then the minimum is gonna be the infimum. Easy to prove. So I'm gonna leave the proof as an exercise if you want. I mean, if you want to, you may prove this for yourself. I will probably reveal the answer of the provings in a text file later. But anyways, for now, I'm gonna just tell you this fact. If the maximum exists, then the maximum is the supremum. If the minimum exists, the minimum is the infimum. That means we're actually kind of generalizing things from maximum and minimum, which is in the set, which exists in the set, to something that's may not be we're generalizing this concept to something that may not be inside the set, but still has this property of describing the range of S. So that's it for supremum and infimum. That's all we have to know here about sets, and then we can go on to functions. To functions that we have not met before. Like the Dirac function and the Riemann functions. But most importantly, we're gonna tell something that you might have heard before but does not really know the definition of, which is, I'm gonna just continue on writing down, fundamental functions. From a basic point of view, there are 6 types of fundamental functions. First is very obvious. Not really obvious, but it's gonna be a function that you think it's gonna be the easiest. Constant. Constant functions means fx equals k, where this k is gonna be a constant. I'm not gonna write k as a constant here, but I'm lazy. So then the next type is gonna be powers, also called power functions. Means f of x equals x to the k, where k is now a constant. K is still a constant. The third type, exponential function. Now, in history, exponential function refers to fx equals some number that we nowadays call e raised to the power x. But now, exponential functions, nowadays, again, I repeat, nowadays, exponential functions refer to some constants raised to the power x. It's generalized one step further. The fourth type is called logarithmic functions. Which is fx equals log x to the base k. K is a constant now, again. A fifth type would be trigonometric functions. Ouch, spelling mistake. Trigonometric function, which is, like sines, cosines, tangents, cotangents, secants, and cosecants. I'll assume you have already get a good grasp of them. Like sines and cosecants are inverses, multiplicative inverses, cosines and secants as well, tangents and cotangents as well, and then you also know the sum to difference. Sum to products, product to sums. What else? Those extended definitions, like if a triangle, not really, if an angle is out of the 0 to 90 degrees range, then how do I define the sines, cosines? I'll assume you already know them as well. So if you don't know them yet, then please go and learn them before you go on to the future episodes, because if you don't know them, it's gonna be kinda hard to comprehend what's gonna happen in the trigonometric functions derivatives. The sixth type is gonna be the arcus functions. Arcus functions, also called the inverse trigonometric functions, because like for sine x, the inverse trigonometric function is going to be called arc sine x, right, with the arc in front. They're called arcus functions by that. These are the 6 basic types of fundamental functions. What else? Is a polynomial a fundamental function? Yes. Then, polynomial is not inside here. Power function is a monomial. It's not a polynomial. Right? Now, fundamental functions does not only consist of these 6 kinds. It can also be the sum, the difference, the products, the divisions, and the composites of these 6 types. Alright. But notice it has to be a finite amount of operations. That means if you're adding an infinite amount of times of a constant function to another constant function, then it may not be a fundamental function, right? Again, if you're adding a fundamental function for an infinite amount of times to another fundamental function, it may not going to be still a fundamental function. Alright? Every single operation, no matter it's addition, subtraction, multiplication, division, or composite, it can only happen for a finite amount of time to ensure that you're still inside the region of this fundamental function. Right? So that's it for today's lesson. I hope you've learned much. Let's review a bit. So first of all, we went through sets, because sets is the basic thing that we have to know in analysis. Before we can go on to analysis and calculus, the real stuff, right, the real bosses, we have to clear up sets. And we learned that there's something called the maximum and the minimum that can tell us about the range of a set. And we defined them. Then we talked about sets that does not have a maximum and minimum, but we still want to properly describe the range of this S. So then we went into upper bounds and lower bounds, but upper bounds and lower bounds may involve something that is useless. So we come up with infimum and supremum and gave definitions of infimums and supremums. So now we have supremum and infimum. We also know that it's going to be a generalization of the maximum and minimums, which means supremum and infimum still conserves what maximum and minimum can do, because if a maximum exists, it's a supremum. If a minimum exists, it's an infimum. Right? It conserves what maximum and minimum do, while also not restricting the upper bound and lower bound of a set, the supremum and infimum of a set, not restricting them to be still inside the set, so that we can still have some kind of way to describe the range of the elements inside S. And then we went through fundamental functions, given the 6 basic types, and told you that if you do some basic arithmetic operations involving addition, subtraction, multiplication, and division, only these 4, as well as including composition, then you still have fundamental functions, provided that the operation is only done for a finite number of times. So that is all about this lecture, and I hope you enjoyed, and I'm looking forward to seeing you next time.